This is part 1 of section 10.2, Series and Convergence. In this section, we're going to define what an infinite series is and its relationship to a sequence, and we're going to start talking about what it means for a series to converge. So an infinite series is defined as the summation of a sequence with an infinite number of terms. That is, if the sequence a sub n is an infinite sequence, then we can define the infinite series in this way. So it's the summation. So the symbol here is the summation symbol, which means you're adding. That's the capital Greek letter sigma. And so we're going to be adding from n equals 1 to infinity of all of our terms of our infinite sequence. So that's why we have a sub n here, and then we're showing that we're adding each term, and it's going to continue indefinitely. So one thing we want to do, though, because we don't want to add forever, is find partial sums. So when we find that a sequence of partial sums converges, then the series will also converge. So that's one of the reasons why we look at partial sums. So in this lesson, we're going to start with some basic series, which hopefully have some familiarity with you, such as a geometric series. And we're also going to look at a telescoping series as well. And then we're going to pick up in the next section on a couple other very common series, which are the piece series and the harmonic series. So infinite sums are called series. So that's what we have in our first picture, right here, our first box. That's an infinite series. So we're taking the summation from 1 to infinity of an a sub n term, 1 over 2 to the n. Now the difference between that and the next one is a sequence just lists the terms. They are not added together in any way. And then the value of a series is the limit of the sequence. So if we want to know what that sum is headed to, it's going to be the limit of our sequence. So our first idea here is to start creating some partial sums. So we have this series, the summation of n equals 1 to n of 1 over 2 to the n minus 1. And we are asked to write the indicated partial sums. So s sub 1 is just going to be the first term, which is 1 over 2 to the 1 minus 1. So that's 1 over 2 to the 0, which is 1. So the second partial sum is going to be my s1 plus the next term. So that is going to be 1 plus 1 over 2 to the 2 minus 1. So I'm going to have 1 plus 1/2. My third partial sum will be adding up what I have so far. So I have to add an a3 in. So I have my 1, I have my 1/2, and now I'm going to have 1 over 2 to the 3 minus 1. So this becomes 1 plus 1/2 plus 1/4. So next we want the nth term. So what we have is we have everything we've done so far, and then we're going to add up all the terms in between, and then eventually add in the nth term. So definitions of convergence and divergence series. So for the infinite series, the summation from n equals 1 to infinity of a sub n, the nth partial sum is given by s sub n, as we talked about, is adding up all of the terms up through a sub n. If the sequence of partial sum converges to s, and s has to be a real number, then the series converges. So let me say that again. If the sequence of partial sums, because we're going to create a sequence of partial sums here, so S1, S2, S3, if they converge to some real number, the series itself converges. The limit S is called the sum of the series. If that sequence of partial sums diverges, then the series diverges. And we're going to use that as a big help for us to determine the behavior of these series. So one of the most common series to look at is the geometric series. So a geometric series is the summation from n equals 0 to infinity of a sub r to the n. It could also be written in the following manner, because we're used to seeing a 1 down there. The summation from n equals 1 to infinity of a times r to the n minus 1. We just shift the index over by 1. Okay, so a geometric series will converge with a ratio r if r is between the absolute value, could be negative or positive. If the absolute value of r is somewhere between 0 and 1, it will converge. If it diverges, then r, the absolute value of r, is greater than 1. Even more so, if we find it does converge, there's a nice little formula that it converges to. It converges to a over 1 minus r, where a is the first term of the geometric series. So partial sums. So you can find the partial sum of a geometric series in this way. So you have a sub 1 minus a sub n times r over 1 minus r, which simplifies it. And this is usually the one that's easy to remember right here. I didn't want to exclude my little a1. So you really have 1 minus r to the n over 1 minus r, and that whole fraction is multiplied by the first term, a sub 1. So example 2. Consider the infinite geometric series a sub n equals 8 plus 8 fifths plus 8 25ths plus 8 over 125. So first we're supposed to find a1. Well, that's easy because they wrote the terms out. a1 is just 8, the first number. Now we want to know what r is. So we have to see what we're multiplying by, because we have this idea. So we need some r here. So if we see every time we have 5 to the first power, and then we have 5 to the second power, 5 to the third power. So our r is going to be 1/5, because that 5 is always in the denominator. So r is going to be 1/5. So now we can write an explicit rule. So a sub n is going to equal, and the way it's written here, I am going to adjust the rule a little bit. So it's going to be 8 times 1 over 5 to the n minus rule. I'm going to bump that index. So finding the fourth partial sum is going to be, so I already have it written up there, I just have to add it. So I have 8 plus 8 fifths plus 8 25ths plus 8 over 125. So finding a common denominator and simplifying, I get 1,248 over 125. So we're trying to find the infinite sum s sub n. So s sub n, using our formula, is going to be a over 1 minus r. So it's going to be 8 over 1 minus 1/5. So when we simplify this, we get 8 over 4/5, which becomes 10. So now we want to find the limit. So we're finding the limit as n approaches infinity of 8 times 1 over 5 to the n minus 1. And when we do this, we're going to see that this indeed goes to 0. So I'm going to stop here, and I will continue in the second video.